Hello everyone, whoever is watching this. I don't know why you watch this, but so today I will be talking about linear transformation in functional functional spaces. Okay, these are some heavy words, and actually I even don't know if this is what they conventionally call it, but I will just say what it means. But before that, I will have to. Okay, I will just say what it means. Suppose you have a real axis, and in this real axis you defined an interval between 2 points, and you are only concerned about the points between these 2 points, and anything else you just are not concerned. And what you did was, okay, let's make a boundary on this. Let's make a boundary. So here is the boundary. uh, okay, so let me just move on. So there are functions between this point, and any function, any finite function is allowed. Any function which doesn't explode to infinity and continuous is allowed. So you can have anything, any function f of x defined between a to b to the mapping, a mapping between real numbers a to b. And the thing is, I want to have a, let's say I have a transformation, I will call it, let's say u, such that when I apply this on on my function, this transformation changes my function to some other function. And what I want to find out is, so suppose you have this function, and this function will have a property such that if I square this and take the area between uh, take the area under this, it will give me some value. I want a transformation such that even after doing the transformation on f of x, the area is present. I want to find something like this. Why? The reason, I have no reason. I just want to find it. I really don't know why. I mean, uh, it just felt interesting, so I just want to find it. And the thing is, what should be, what criteria should this follow? Should this transformation follow? And the idea is pretty like, and we can actually, uh, it is not hard to find this, what exactly this is. So it becomes more simpler to understand if you think everything in terms of vectors. For example, you know that in 3D you can write a vector something like this, x y z, and at every point you have some values defined. You can do the same thing actually on real numbers, right? Like, let's say you have x, but the problem is, you so basically you have a number defined at every point here. So difference is, for an n dimensional finite vector, uh, you have like this, something like this, and you have a number defined uniquely. But actually you are doing the same thing here. You have a unique number defined at every place. So basically, if you consider the position anywhere on this number line as x, you will have some value assigned on that position f of x, and that's more than enough for a vector. You have f of x. F of x is a vector. A function itself is the vector, and f of x plus g of x will also be a vector. So we have this nice properties. I mean, we have this nice things going on. Like, it's just a vector. A function itself a vector between only the function defined between a and b. And you can have dot products as well. You just do this dot product between two functions. This functions are vectors, so you just do this. Here, this thing will be called as weight. Uh, it is just a factor to make sure the dot product doesn't explode. So this will be your dot product, and I'm keeping everything real for now. Everything will be real. So everything will be real, and everything, all the functions will also be real. Everything is real. So uh, and so yeah, so also you know that uh, how does a vector transform? You just have some matrix, let's say u of ij, and you have v1 v2 some vj. You just to do this, right? Summation u of ij uh, vj, and this gives you some new vector, let's say wj. Well, we can do this the same thing here. Here it will correspond to a function something like this xx dash. You can think this as the uh, how should I say, rows, and this thing as the columns. So basically a new vector, I mean a new function I will get after some transformation will look something like this. So this is the transformation I applied on f of x. Now so yeah, what should be this u, like what all should this u satisfy? There is no u dash here. What all should this u satisfy such that when I get f of x, capital F of x, when I get this new function, after transforming the older one, whatever area I had in this older one, like it's square, it should be the same for this one. That's the question. And this we have another analogy for this as well. So basically if you have a unitary matrix and you apply this on a vector, and you get another vector, let's say uh, v prime. The good thing is if we the magnitude remains preserved because of unitary vector, and the speciality of a unitary vector is that all uh, column vectors inside it are orthogonal to each other. I can do the same thing here. Basically I can write this something like this, you know, u of let's say uh, ith column and some jth column, and they are just getting summed over, and this will be okay. I have to be careful, I think. Yeah, they are getting summed over, right? In the rows, they are getting summed over in the rows. So ith column and jth column, and this will be my delta ij. I can do the same thing here. So I just have this unitary matrix, and I will just uh, multiply this with so let's do this. Let's say I have some point here, some position, and I multiply this to some other position. So basically this will correspond to the column, to that particular column. And when I do this and integrate this throughout, I should get this. This should be the criteria I should be following if I really want a unitary transformation. So I am thinking what all can it be, like what function can it be? I'm just thinking any particular function does it for satisfy this. Nothing right now I can think of, but uh, so there can be a lot of them, but right now I don't think I can think anything in mind. So what this is saying is, if you have this function u, whatever this function is, let's say this is my function, I need some u, that u of x and x prime. Yeah, also this is a text. For if I change the x prime, the shape might vary a little. I'm just keeping the x prime fixed, and let me write this neat basically you have u of x prime, and let's keep this fixed. So this is telling me that at a certain x, at a certain value x1, at a certain value x1, and at some other value x2, uh, and vary the x prime. So if I vary the x prime, it can so basically for different values of x prime, keep changing this, multiply them together and just add them up, and if I successfully get this, then my area will be preserved. So I want to find a particular example of this and check if this really works. So one of the example right now I can think of is, I don't know, mm, let us see. So actually the most trivial one will be this itself, x minus x prime, and you can see how why. So like so let's use this, like if I transform this, I will get my function back. So in a sense this is a actually like an identity transformation, and so this here is the equivalent of identity transformation in this space. And now um, uh, and now anything else can we think of? That will be a good question. So also I think it is safe to say that the matrix here, whatever we call the matrix there, we can kind of call this density function, this quantity which we are using. It is also a matrix actually, in a sense, like it's in the continuous domain. Really nothing more than that actually. Whatever we are doing there, we can do the same thing here, of course. And I think we can also see it, like you can think of this matrix like a scalar field actually. So basically you have x here, x prime defined here, and suppose we are only concerned about a's and b's, and we have this. So we have a scalar field defined on this region, and every point in space in this, and when you are doing when you are applying the operator, when this scalar field itself is the operator on my function. I just take the function, uh, the value of that function, and I just um, analyze it on every point and just add them all up, and I get a new function out of it. I think it will be not like this but like that. It doesn't matter, but it does matter actually. So something like this. I will do this for all the x primes, and depending on what my x value is, I will get a function on different uh, places here. The integral throughout x prime will be done. So now uh, I want to find a non-trivial example which I really don't have in my mind. Like, what can it be exactly? Uh, the problem is, of course, like finding a function which satisfies these conditions. Anything that does this, I think, will be good enough for me to solve, find the function, which non-trivial function, which is not a delta. I wonder if I can do anything with these. Uh, you might have seen them, but let me write delta. L is equal to b minus a. I wonder if this will help, but so if I do this, this actually always gives me uh, delta of m comma n. No, this will always give me. Sorry, I think I should write sign here. This will be better. Yes, there should be a sign here. Now this is better. If I do this, I know this is the case, but hmm, and I'm pretty sure some constant numbers come here, but we will leave it for later. We can just send it there. So what to do? What to do? So yeah, I used AI. So I think this is one of the example it's showing me. Kind of like weird. I don't know. Like if that works, then why not? Hmm. So I don't know how will I set this for the. I think I can do that. Set it for the limit. Let us use this itself. Whatever they are saying. I can't sit all night and day to find this thing, but I would be interested to check if it really works. So Fresnel kernel, that's what we call it. Fine, a kernel. Okay, I think this is nice. Kernel. Okay, so remember from matrix, from finite, from vector space to functional space, a matrix uh, gets transitioned to a kernel. So now I want to check if this thing really works. So square root 1 by I by v e power, I don't know what is this all lambda and everything, but let's see. And I assume that this is like for minus infinity to infinity, but I can take care of that since my function is 0 outside a and b. I can take care of that. So I think I have to just use this, do this, right? F of x square root of 1 by I lambda z e power I pi lambda square x minus x prime square. I am not convinced that how this will really give me the area preserved if I do this, which is confusing in itself. Not confusing. You get confused when you have some initial data and you just are not able to figure out what to do with it. That's confusion. But if you don't have anything in the first place, how are you even confused? If you don't even know anything, what does confusion mean. So now so uh, now mm, let me check how does this work. I think I should just check if this at least area gives me one. That's the least I can do. And uh, I think they are considering, okay, they are actually considering the complex space. I don't want to use the complex space, but I think that is all we have got. So if you do that, let me just check. So u star u dx, that should give me delta x minus x prime. Will I get that? 1 minus uh, lambda, 1 minus lambda z e power I pi by lambda square. It will be x plus x prime. No, it will be actually 2x prime and 2x, and you are doing this x with respect to x or x prime from minus infinity to infinity. And I know that I know this property that e power I kx dx minus infinity to infinity, this just corresponds to a delta function. I don't know how to rewrite it, but okay, fine. I guess that's all for today. Bye.